today? No? Okay. Okay, so increasing, decreasing, we'll put it back on the top so it knows it's the right one. Yay. We're going to first find the domain. We're doing number 2. Alright, with exponential functions, what does a e to the x graph look like? Okay, so we have a horizontal asymptote, and it looks like that. Okay, if the negative is in the exponent, what does that do to the graph? It's not in front of the e, it's in the exponent. Okay, why don't you graph it, see what happens. E to the negative 3x. E to the negative 3x. Okay, let me do it here. E to the negative 3x graph. Oh, this is a weird graph. Okay, so that negative does what? Yep, it rotates around the y-axis, so it becomes this red one, like that. Oops, I guess I should write a new graph, because that would not be equivalent. Yep. Okay, so the domain of this function. Ariel, what would the domain of this, the red function be? I think that's the range. Well, 0 to positive infinity is the range. Domain is the spread horizontally, but this arrow means it keeps going. But domain is just the x values. We're not looking at heights, we're seeing the spread on the x-axis. Okay, so negative infinity to, there you go. Okay, so the first part A, the domain, is you can also say all real numbers, or you can put negative infinity and positive infinity. Those are parentheses because we never actually reach infinity. Right? dy dx. Part B, finding dy dx. So if we take the derivative of f of x, how do we notate the derivative of f of x? That's one way to do it, f prime of x. Equals the derivative of e to the x, remember, is itself e to the x. So this is a little bit of chain rule. F of x is e to the x, g of x is the stuffing, negative 3x. The derivative of e to the x is itself. That's a really nice derivative. And the derivative of negative 3x is negative 3. So who can tell me the derivative of e to the negative 3x? So we have e with its stuffing, negative 3x, times by the derivative of g, which is just negative 3. And it looks a little prettier if you put it in the front. Yep. Okay. Alright, so we found dy dx. Now we're going to find the critical points. Well, what does dy dx actually look like? This is our dy dx, by the way. Dy dx. Actually, well, since we don't have y, it'd be more technically df of x dx equals negative 3 e to negative 3x. What does that graph look like? We have the negative in the exponent, so it looks similar to this red graph. So now it's going to take that red graph and flip it over the x-axis so it becomes something like this. Okay, so the critical points we're looking for when the derivative is 0 and when it's undefined. So when is dy dx or df of x dx 0. When does that happen? When is this derivative 0? When I say 0, am I looking for an x being 0 or y being 0? So your y being 0. When does this graph have a y value of 0? It doesn't. There's a horizontal asymptote. So there are none. No critical points. Okay, the other thing we have to look for is when do we have a restricted value? Meaning, when do we have a vertical asymptote or something undefined? Yep, this is also none. That really happens more with fractions, right, when the denominator is 0. Okay, part D, we're going to draw a number line for our derivative. And using the critical points, we would label the critical points on our number line. What are the critical points we found in part B? Did I skip C? This is C, part C. What critical points did we find in part C? None. So there's nothing to put on here, okay, on our number line, because there's never a change in sign. What's always happening with this derivative? What's the sign of this derivative always? Negative. So the derivative f prime is always negative, meaning that the position function was, the original function was always decreasing. And E is the answer. F is always decreasing. Do you remember how we did this last time? Because, how can we prove? Because f prime is less than 0. Okay. We finished number 3, right? Okay, let's look at number 4. And then I have one to add on. I don't think that's on your paper. Number 4, and it does have an asterisk that says do it graphically. Okay. G of x equals x to the 1/3 times x plus 8. Find the domain. This is a parent function that hopefully you know. What does, and if you don't know, you can break it up piece by piece. X 1/3 means it's a, what type of function? Cube root. What does a cube root function look like? Square root looks like that. Cube root looks like that, right? Okay, and this is being times by something that is linear, x plus 8. What does x plus 8 look like? It's linear, and it crosses at 8. Okay, so it says, what's the domain? What's the domain of x to the 1/3? A cube root function. Negative infinity to positive infinity. What's the domain of this linear function? The same. So if we were to multiply them, what's the derivative of the combination? What? Then it wouldn't be negative infinity to positive infinity. It would depend on the function. I don't think I can really answer that until we have a function. The next one's also.
So, there was a hole somewhere. Do we see if there can be there?
So if like we had a square root or something, right? So square root of x, and the other one being multiplied was our linear function. This one is negative infinity and positive infinity for the domain. And this one is 0 to infinity. Okay, so when we put them together, can we put any x value in for that square root? No, what's the smallest value you can put in? 0. So the domain would have to take this domain. The other one, the linear, can take any x value. But we have a restriction right there. Okay, that's actually a really good question. So that was a side note. Erase that. So our domain for number 1, or part A, I guess we're really in A. The domain, oh, the extra stuff too. Would be 0 to, oops, that was the fake function I made up. Okay, negative infinity and positive infinity. Now we're back to the normal function. Okay, part B, it wants you to find dy dx or g prime. Okay, you have a couple options here, I guess. What are some ways you can take the derivative of g of x? You can do product rule, first you last plus last you first, or you could, it's not a function inside a function. You can't, no, exponential rule would be when the exponent is an x. Distribute, and then treat it like a polynomial and use the power rule. Okay, so choose one of those and take the derivative. There's a fraction involved, so you have to know how to work with exponents. When dealing with these exponents and the base is the same, when you multiply exponents, what do you do with their exponent? You add, multiply, add. If you're choosing distributive property, you have to know how to add the exponents. A little challenging with that cube root, right? Okay, who chose to distribute? Only a couple people. Okay, so the rest of you did product rule. Okay, if I distribute, I'll do that one first. If I distribute g of x, I get x to the 1/3 times x to the 3/3. I'm going to put that so I can visually see how to add them. Plus 8 times x to the 1/3. So as long as I have common denominators, I can just add those. We get x to the 4/3 plus 8x to the 1/3. So g prime would be 4/3 x to the what? 1/3, because you subtract 1, meaning subtract 3/3, plus 8/3 x to the negative 2/3. And I saw you went into the root form because the negative would put it down in the bottom and be a cube root. Okay, if we did product rule. Oh yeah, you can. Product rule also asks for a specific form. G prime of x, first. G last, what's the derivative of x plus 8? 1. Plus last, G first, the derivative of x to the 1/3 power is 1/3 x to the negative 2/3. And so we get x to the 1/3 plus 1/3 x to the negative 2/3 times x to the 3/3 plus 8/3 x to the negative 2/3. I think you end up getting a like term, right? Don't these both become 1/3? Yep. And then it becomes that because 1 plus these are like terms, you get 4/3. Okay, now let's see what that looks like on our calculator, because this is kind of an awful one. Because the next step, we were looking for roots, right? Zeros, critical points. So we have to know what this graph looks like. So I'm going to go to the next screen. Oops. And everyone still have their calculators out? Go to y equals. And what I want you to do is put the original function in y equals. Yep. So make sure you put parentheses around that 1/3 times x plus 8. I think we briefly looked at this once before, but I'm going to have y1 as the original and y2 I want as the derivative. You can hand type in what you did, or you can let the calculator figure it out for you. Do you remember how to have the calculator graph the derivative? I think we've done this once. Remember when I didn't know how to use the old school calculators? The new ones we were getting to work, but the old ones we weren't. It's under math. Go to math and find n deriv. It looks like it's number 8. If you have one of the newer calculators, yours format's a little nicer than mine. Who has the old version like mine? Okay, if you have the old version, we need to put in 3 things. We put in the original function, comma, x, comma, x. So you can hand type everything in, or this original function is called something. The original function is called y1. Does anyone know how to get to y1? Use this a lot in secondary math 3 when you're doing a regression. Remember how you get your y1 function? It's under vars. See the vars button next to the clear button? Vars. Arrow over to y vars. Function y1. Or you can hand type all of it in again. Those with new calculators like you, so I can see you have a new one. Do you know how to type yours in? Here, okay, yeah, let's show this one on the camera. Oh, yeah. Yours is a fun setup. It's actually way easier though. So his says I'm going to take the derivative of d sub x. We'll put our variable x there. And then in the parentheses is your y1. So again, you can type all that in, or you can go to vars. Then what do I go to? Y vars function f1. And now this line x, that's what you're evaluating at. So if you want to evaluate the derivative at, say, x equals 3, you'd put x equals 3. But for us, we just want x equals x. Just all x's. Okay, there's yours. And so same with mine. I'm going to put comma. I'm taking the derivative with respect to x, comma. I'm evaluating on all x's, because I'm not evaluating a specific x. So if you have the old version, it's n deriv y1, comma, x, x. Okay? And hit, oh, by the way, I want to, on y2, go on to the far left. See how they're both skinny lines? I want to see them differently. So if you push enter, you can change to like a thicker line. Sometimes you have to hit enter a couple times so you see a thicker line. Yep. Yep, so if you're like doing inequalities or something, you can have it shade. Okay, so I will know that my thicker line is my derivative. So go ahead and hit enter, and sometimes it's calculating the derivative as it's graphing, so sometimes it's kind of slow. That's the original. Here's the derivative. Okay, so if I go back to my notes really quick, let's roughly sketch what the derivative looks like. Actually, we need to find on our graph. For part C, to help sketch this, let's find the critical point. What does it mean for critical point? Y equals 0. On my derivative, does y ever equal 0? Yes. When y equals 0, you're crossing the x-intercept, the x-axis. Right there, y is 0. Okay, so go to your calc feature. Second, calc. How do you find a 0? What? Number 2. Now, if you right now, you can see mine is on the skinny line. So I think it's just up and down. And if you go up or down, you can jump over to the line you want. We want the thick line for the derivative. So left bound, make sure you're on the left, which in this case means you're underneath the x-axis. Push enter. You can see how that little arrow pops up? You want to get these two flapping arrows so that they're pointing towards each other. If one's pointing the opposite way, you're going to get an error. Okay, and then I go to the right until I am to the right of the intersection. And I have two pointing arrows towards each other. It says somewhere in this gap is value, and I want to really get my cursor, it says guess, as close as possible. So I hit enter again. And what's the 0? -2, comma, 0. Okay. Are there any places where we have restricted values because the derivative is undefined? Right, maybe let me make the original. Actually, we don't even need the original anymore, so I can turn it off. Do you know how to turn off your original without erasing it? Yeah, you just unerase the equals, and I'll make this one a skinny line again so we can maybe see it more clear. Okay. When it does the derivative, it's really slow. So just have patience. Where at? Okay, we do have a restricted value at x equals 0.
Well, because the negative is proof brings the x to the bottom. That's why you have a 0 at the bottom, right?
Yeah, so let's look at our derivative again. Yeah, so we have, I should probably go right on the board instead of writing with the mouse. G prime of x equals, we have this guy on top, and we have this guy on bottom. Let's see, cube root of x squared. Okay, our restricted values are when the denominator is 0, right? And the only thing that would make this 0 is x being 0. Okay, so on our graph, we have a critical point at -2, and I don't remember what it did. Let's see what it looked like. It was curvy, and then we did that. Okay. And it shoots up, and then it does something like that. But there's two parts you should get from the graph. -2 is a critical point. This is part C. We have a critical point at x equals -2. And right here we get a vertical asymptote because our restricted value, the denominator, can't be 0, yeah? Are you on your table? You're on y2. And that's the derivative. Well, you can't divide by 0, though. Yours is also on inequalities. What do you have at -2? See, -2 should be 0. I don't know, I have to look at that. Okay, restricted value at x equals 0. Because f prime of x is undefined. Right there. Now we're going to draw a number line for f prime. And we have to mark on our number line our critical points. Oh, thanks. And our restricted values, because something happens at these. G prime of x, remember you're looking at the derivative. That's why it's nice to be able to sketch the graph. From -infinity up through -2, what's the sign of the graph? Negative. After -2, what's the sign of the graph? Positive. After 0, it's positive. Negative. But that's the derivative is decreasing. Because it's positive, the original function, g, is not decreasing, it is increasing. Okay. Yep. So that would be more of the acceleration, right? Okay, so here we have our f function be decreasing, increasing, increasing. So for part E, we're going to write our intervals of increasing and decreasing. So g of x is increasing on what interval? No, actually, it's not -2 to infinity. 2 to 0, union 0 to infinity. Because right at -2, it's changing. That's a 0, so your tangent line is horizontal. It's changing from increasing to decreasing. And g of x is decreasing on what interval? -infinity to -2. Parentheses, because right there at the 0 is when we get a horizontal tangent line that's changing from increasing to decreasing. Okay? Now, I don't think you have this last one. Is that the end of your notes? Let's just do one more. If you could just get a piece of paper and attach it to the notes. Let's look at a trig function, and then we're going to spend the rest of the time working on derivatives. Derivatives. Okay, number 5, same thing. We'll go find the intervals of increasing and decreasing. This is the first derivative test, helping us, we do the derivative to see when it's increasing and decreasing. Say what? Yeah, that's pi thirds. And 5 pi thirds. So this is our function. Y equals cosine of x minus pi thirds from 0 to 5 pi thirds. 0 is less than x, which is less than or equal to 5 pi thirds. So part A, first think about the domain. What do cosine functions do? Good job. We learned that last time, right? Cosine functions is a wave, goes up and down, oscillates forever. But when you say the domain, it has to be off of what is given. Does this say, look at the function for all real numbers forever? And this one has an equal to, this one does not. So what would the domain look like, Joanna, if this one has no equal to and this one has an equal to? Okay, so parenthesis, but what are my numbers? With a, good. Okay, dy dx. Okay, this is chain rule. What's the derivative of cosine? Negative. You have to have a negative. Sine of the stuffing times by the derivative of the stuffing. What's the derivative of x minus pi thirds? Times by 1. So I'm not going to put times by 1 because it doesn't really do anything. Okay, critical points. Critical points are we're looking for where the derivative equals 0. And restricted values, we're looking for where the derivative is undefined. So, is sine, a negative sine curve, ever going to hit a 0? Is it ever going to cross the x-axis? Definitely. Definitely. And this minus pi thirds is a specific shift. Remember? Opposite? Same. Outside is same. Inside is opposite. Vertical is outside. Inside is horizontal shift. Yep. So that is a horizontal shift right pi thirds. So when we start looking at the graph to find critical points, we have pi thirds. Okay, it goes till 5 pi thirds, it looks like. So here is 2 pi thirds, 3 pi thirds, which is just pi, right? 4 pi thirds. The reason they want us to go out to 5 pi thirds is because if we shift it to the right, the period ends at 5 pi thirds far. Well, normally it would end at 6 pi thirds, huh? The normal cosine function looks like this, from 0 to 2 pi, and 2 pi is the same as 6 pi thirds. It goes like this, right? Okay, so, except for we're not actually graphing cosine, we're graphing sine. Negative sine starts at a, oh, yeah, sorry, I was thinking cosine again. Sorry. Okay, and every pi has another 0, right? But negative oh, that's not pi. I put the the point on the wrong spot. Pi thirds plus pi is 4 pi thirds. The point should be there. Okay, since it is a negative sign, it goes down first, and then up. So we hit a minimum here. What's the amplitude of this? One. Amplitude is 1. Okay, so we want to know critical points. Where do we hit zeros? And it's only from the interval from 0 to 5 pi thirds. So where are the zeros at? Pi thirds and 4 pi thirds. So the critical points at x equals pi thirds and 4 pi thirds. Okay, do we have any restricted values? Because we have something undefined on our derivative. Any restricted values? No. It just continues forever. So restricted values are none. Okay, so now part D, we draw a number line to look at our intervals from increasing and decreasing for our derivative, which is, function was y, so I'll put y prime. Based on your restricted values or your critical points, which we don't have any restricted values, we just have critical points. I don't know why I keep writing a 5, it's definitely not 5. Pi thirds, 4 pi thirds. How from 0 to pi thirds, what's the sign of the graph? Positive. So that means the function is doing what, Hala? Good, increasing. Then here we see it's negative, and then it goes positive again. So we have increase, decrease, increase. Okay. Now, we've done this before. When we're changing from increase to decrease, and then we've just mentioned on the last problem, this 0 becomes what? And this function technically goes on forever, but we've restricted the domain, so this is called a relative. If it's increasing and then decreasing, it'd be a relative max. So we have a relative max. Okay, do we know any relative mins? 4 pi thirds, because it's going from decreasing. Okay? And on our domain, we also had an open circle there, and then at 5 pi thirds, remember we had a bracket. Okay, so intervals of increasing to decreasing. Y is increasing from where to where? And it's not negative infinity. And we're not including 0, so it's open interval 0, comma, pi thirds, union, 4 pi thirds, comma. What do we put on 5 pi thirds? A bracket. And we know this because y prime is y is decreasing from pi thirds to 4 pi thirds because y prime is less than 0. Okay. Okay, for the rest of the time we're going to be working on your blue derivative packet. I hope you've been studying those. I'm sorry? We can turn it in next time. I want to work on derivatives. Okay, questions on this I will take next time. On, I think so. So your blue packet called all kinds of derivatives. Would you quickly pull that out? Are there any that you're stuck on? Yes? Number 7. Okay, this is going to be the quotient rule, right? So, when I say quotient rule, I always set it, and always set these up in the same order. F is on top because it's representing numerator. G is on bottom because it's representing denominator. And then you have to have F prime of X and G prime of X. Okay, Alex, what's the derivative of e to the 3x? The derivative of e to the x is just e to the x. So the derivative of e to the x is itself, but we have a little bit of chain rule, so we have to times by the derivative of that exponent. What's the derivative of the exponent? What's the derivative of 3x? It's 3. So it's just 3e to the 3x. So it's itself times the derivative of the exponent. Okay, read what's the derivative of g of x? G prime. What? Yep. Okay, so we do quotient rule. Y prime, you have to be saying y prime or dy dx. Okay. Equals ho d high. What comes next? Minus high d ho over what? Ho ho. And for our purposes, we're just stopping here, squared, just to see that you can set it up correctly. Something to help you maybe remember some of the trig functions. We've been trying to find what ways to help you remember. So trig functions are the big secret, right? So you turn to your neighbor and go, psst, I remember them. Do you? Psst. And then you ignore the S. Secant, I have it over here on the board. Secant, tangent. So if you want the derivative of the secant, it is secant times tangent. If you want the derivative of the tangent, it is secant squared. See the arrows? Okay, then we have cosecant and cotangent. It does the same thing. The derivative of, not cot. What? Cosecant. 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 Derivative of cosecant is cosecant cotangent. Derivative of cotangent is negative. Sorry, this needs a negative. That needs a negative. Negative cosecant squared. Okay? Maybe that will help you. Okay, let's find another one to do here. What about number 16? You can do product rule galore on this, but there's an easier way to do it. Number 16. Remember, this 4 means we have 4 tangents of 2x plus 3. So you can make it into a polynomial. That's the trick. You got to make it into a polynomial. Notice I'm bringing down my equal sign so I have equivalent statements. What would the f of x function be if I'm thinking chain rule? X to the 4th. Good. It becomes a polynomial. G of x is your stuffing. Tangent 2x plus 3. Okay. Rebecca, what's the derivative of f, or f prime? Good. That was too easy, Rebecca, so I need to give you a different one. What's the derivative of g? We have another chain rule, right? Remember tangent? Tangent going this way becomes secant squared. Okay, so great. Okay, so our y prime how's it go? Chain rule. F prime with the stuffing g of x. Now don't forget that this f prime had a cubed times g prime. 2 secant squared of 2x plus 3. Because it's chain rule, again. The derivative of 2x plus 3 becomes 2. Okay, let's see. 22? Okay, I've done the whole packet, and I felt like, because I did it all in one sitting, and I felt like afterwards I was like, whoa, brain overload. I felt like I was doing the same problem over and over, because there's lots of repeats with slight differences. Okay, and this is the one that kept coming up. There's lots of constants that sneak in. Something here is a constant. Yeah, and every time I saw a constant to remind myself, I just put a little arrow, and I told myself, that's a constant. So when I take the derivative of it, it's gone. 0. Sine pi is a constant. Okay, so, which number was this, 22? Now, x is in the exponent of the exponential. I like e's because we have a little, you can do the exponential we did last, or 2 times ago. But I like e's because it's just an easy chain rule. Our f of x is e to the x, and the derivative is itself. All we have to do is times by the derivative of the exponent. What's the derivative of the exponent? Negative sine x. Okay, so when we're finding y prime, we have e to the exponent, the stuffing stays the same, but we times by negative sine x. And we generally like write that in the front, but you can write it after as long as you're clear that you're you're multiplying. This is chain rule again.
So how do you choose the chain rules?
Because it's easier for me.
But we can do it.
You can do it the other way. I just like chain rule because I know e to the x's will be itself, and all I have to do is times by the derivative of the exponent. Okay. Let's find another doozy. 57. Okay. I really think each time you should, even if you think you can do it in your head to avoid mistakes, I think you should write out your f's, your highs and your lows, and take the derivative of each of them. 2x plus 5 e to the 3x. See, this is another repeat. We've done this problem 3 times today. One time it was a negative 3x. The last time we've already done e to the 3x. It's a repeat, so you should get more and more comfortable with your e's. F prime of x equals 2. G of x, we're going to have Kyle do this one. G prime. What's G prime? If that's good. So that Derivative of 3x just becomes a multiplier. Derivative of 3x is 3. Okay, so if we have those set up, we do quotient rule. Anisha, what do we get with quotient rule? So can you tell me specifically what to write? All over. Good. Okay, I have all the answers for you to take home. We will be having our second derivative test. You have to practice, practice, practice these. Do you want to take one for Ethan? Are you going to see Ethan? Anyone going to see Ethan? Okay, I'll give you an extra one then for Ethan. 4, 5, 6. Yeah, I'll take 4, 4 next time, and questions on 5, 2 next time. Okay, see ya. Okay, you have to get a bunch of these rows are being gone too. You need to do a tutorial. Okay. Okay, so these have all the work. By the end, I started doing it in my head because I got a little tired of showing all the steps.